Imagine for a second that you just finished recording this hour-long voice memo, or maybe a really intense conversation.
That's right, just raw audio.
Exactly, just raw audio. And you take that file, you press exactly one button, and then you just walk away. Like you literally leave the room, go pour yourself a cup of coffee.
Dream scenario.
It is, because by the time you sit back down at your desk, your laptop has just autonomously transcribed the entire thing, mapped out who is speaking when, generated all the metadata, animated this fully rendered video visualization, and published it directly to YouTube.
And did all of that without sending your actual audio file to some massive cloud server?
Yes. That is the crazy part. It keeps your data completely private, totally offline, right up until that final video file hits YouTube's server.
Which is, frankly, kind of unbelievable when you look at how standard AI workflows operate today.
It really is. And so for today's deep dive, we are opening up the black box of this leaked pre-release concept paper. It's dated May 17th, 2026. And it makes this kind of extreme automated developer magic an actual reality. We're looking at a highly opinionated local first tool called the audio-to-video pipeline.
Yeah, and the opinionated part is doing a lot of heavy lifting there.
Oh, absolutely. So we're going to break down the beautiful and honestly sometimes really messy architectural decisions that make something like this function on just standard consumer hardware.
I think the most important context for this entire document is right at the top. The status is explicitly labeled as draft pre-open source review.
Which is such a vulnerable stage for a project.
It really is. It's this very specific, almost awkward phase in the software development lifecycle. It's the exact moment right before a developer scrubs out all their, hard-coded personal file paths.
Right, all the embarrassing shortcuts.
Exactly. They haven't sanitized the duct-tape workarounds yet. They haven't made it look pretty for the public GitHub repository. So looking at it in this completely raw state, it offers just an incredible case study in systems design.
Yeah, it shows how developers actually handle the brutal realities of running these heavy machine learning workloads locally.
Right, without unlimited cloud budgets.
Exactly. But before we get into the how of this pipeline, I think we really need to look at the why. Like, what is the fundamental structural problem on the internet that even makes a tool like this necessary?
Well, it comes down to a really glaring disparity in the creator economy right now.
Yeah.
If you are someone who deals in pure audio podcasters, audio essayists, or maybe you're using something like Google Notebook LM to generate those synthetic audio deep dives.
Right, which are everywhere right now.
They are. But the underlying architecture of algorithmic discovery, so platforms like YouTube, Instagram, TikTok, they are fundamentally hostile to pure audio.
Oh, completely. They're built entirely around visual retention.
Exactly. The algorithms driving those recommendation engines are optimized for watch time, right? And watch time is inextricably linked to dynamic on-screen changes.
So you can't just upload an MP3 file to YouTube.
No, you literally can't. And even if you just slap a static image over the audio track and make it an MP4, the algorithm basically buries it. It doesn't satisfy the engagement metrics.
So audio creators are effectively forced to become visual media producers just to survive algorithmic irrelevance.
They are. And translating an hour of audio into an algorithmic-friendly video is a genuinely grueling manual workflow.
It is exhausting to even think about. I mean, typically you have to take your finished audio, import it into a massive non-linear video editor.
Like Premiere or Final Cut, yeah.
Right. Then you have to find some background visual that loops nicely. You have to run the audio through some cloud transcription service, download the SRT file, import those subtitles, meticulously align them so they match the voices.
And then comes the rendering tax.
The rendering tax is the worst.
Yeah.
You lock up your machine's resources for an hour, just exporting the final video file.
And you're still not done.
No. Because then you're logging into YouTube Studio, waiting for their chunk processing to finish, manually typing out descriptions, and the worst part, scrubbing through your own timeline to manually log time-stamped chapters.
The operational overhead just completely eclipses the actual creative act.
It does. It really does.
And that is the exact friction point this pipeline targets. It's built as a one-click automation engineered specifically for solo creators or small teams who want to bypass that manual workflow entirely.
But what I found so fascinating about this concept, paper-like, honestly, it's a masterclass in software engineering, is its scope discipline.
Right. What it refuses to do.
Exactly. The author defines the boundaries of this tool not by the features it has, but by the features it ruthlessly rejects.
Because feature creep is the absolute death of open source projects.
It really is. You know, someone builds a great transcription tool and suddenly a user opens a pull request asking for, I don't know, live streaming support.
Or dynamic thumbnail generation.
Right. And before you know it, the core stable functionality is just buried under this unmaintainable mountain of dependencies.
So this pipeline just explicitly rejects all of that. Doesn't do any audio editing.
Not at all.
It operates on the strict assumption that the input audio is already broadcast ready.
Yeah, it's like having this amazing automated car wash, but the car wash explicitly refuses to fix your engine or touch up your paint. It just takes the finished car, washes it, and drives it to the showroom.
That's a great analogy. It won't apply a noise gate, it won't normalize your loudness, and it definitely won't edit out your ums and us.
Which is a brilliant architectural boundary if you think about it.
It is, because it offloads the entire domain of digital signal processing DSP back to the user, or to upstream tools.
Right, because the paper mentions it expects files potentially generated by Google Notebook LM.
Exactly. And those files are already perfectly synthesized. They don't have artifacts. By refusing to touch the DSP domain, the pipeline completely avoids integrating heavy audio libraries that almost always conflict with machine learning dependencies.
But the non-goals don't stop there. It doesn't generate the audio itself. It won't design a custom thumbnail, though I think it says you can provide one if you want.
Yeah, you can point it to an image file.
But it strictly operates as an offline bash process. Zero live streaming support. No translation module. The language you put in is the language you get out.
But the most aggressive limitation.
Yeah, the distribution one.
Right, the absolute refusal to support multi-platform distribution.
I really struggled with this one. The document explicitly says it targets YouTube and YouTube only.
Strictly YouTube.
Which seems insane to me. I mean, bypassing Instagram Reels, TikTok, Spotify video, isn't that a massive missed opportunity when short-form vertical video basically runs the internet?
It seems counterintuitive on the surface, definitely.
Okay.
But you have to view that limitation through the lens of long-term software maintainability.
Okay, walk me through that.
So every external platform you integrate
Mm.
requires you to maintain a persistent connection to a distinct API endpoint. And APIs are incredibly volatile. TikTok changes its authentication flows constantly. Instagram deprecates legacy endpoints without much warning. Spotify alters their video ingestion rules.
So if you're just one developer trying to maintain a bridge to 5 different platforms?
The tool will inevitably be broken for at least one of those platforms on any given day. It's an endless game of whack-a-mole.
Ah, I see.
So by anchoring the pipeline solely to the YouTube Data API v3, which is honestly probably the most stable, mature video API on the internet, the developer basically guarantees high availability. They reduce their maintenance overhead to almost zero.
Okay, so it's defensive architecture.
Exactly. Building a moat against external volatility.
I can actually really respect that. Okay, so now that we know what it won't do, let's pivot to how this machine actually executes its core job. Because it makes a profoundly contrarian choice right out of the gate.
You're talking about the local first approach.
Yes. In a tech landscape that is completely dominated by cloud computing, where the default instinct is to just push heavy AI tasks to massive server farms, this pipeline runs 3 out of its 4 stages completely locally.
Completely offline. It fundamentally rejects cloud transcription and cloud language models.
Which completely changes the constraints of the entire system.
It does. You're no longer operating with the effectively infinite memory of an AWS cluster. You are suddenly bound by the thermal limits and the RAM limits of a laptop sitting on a desk.
And the paper makes this specific hardware optimization choice that basically defines the tool's whole identity. It is explicitly designed for Apple Silicon CPU inference.
Right.
And it aggressively, stubbornly rejects GPU or CUDA optimization.
Which is a huge statement in 2026.
Right. Because NVIDIA GPUs and the CUDA architecture, they are the undisputed bedrock of modern AI. If you run matrix multiplication on a dedicated GPU, it is orders of magnitude faster.
Oh, absolutely.
So intentionally building a heavy machine learning pipeline and saying no GPU optimization allowed feels like, I don't know, it feels like buying a sports car and intentionally ripping out the turbocharger. Why limit this to the CPU?
Well, the decision actually becomes very logical when you realize the developer is prioritizing portability and compatibility over raw bleeding-edge speed.
Okay, how so?
Configuring a consumer PC to properly leverage GPU acceleration is a nightmare. It is a notoriously fragile process.
Oh, tell me about it.
You have to match your specific NVIDIA driver version with the exact right CUDA toolkit, Then you have to make sure the PyTorch binaries align perfectly with that.
And if one dynamic link library is out of place, the whole thing just crashes.
Exactly. It is the primary reason that so many open source AI tools fail to even boot up on a regular user's machine.
Right.
So by targeting Apple Silicon instead, the developer is leveraging Apple's unified memory architecture.
Which is fundamentally different from a PC setup.
Very different. On an M-series Mac, the main CPU and the integrated neural engine share the exact same massive pool of high-bandwidth memory.
Right, so let me break this down for a second. On a traditional PC, you might have, say, 32 gigabytes of regular system RAM, but your graphics card might only have 8 gigabytes of specialized video RAM, or VRAM.
Yes, and the AI models have to fit into that smaller 8-gigabyte VRAM pool to run fast.
Which is a huge bottleneck. But an Apple Silicon machine doesn't have that divide. It allows the model to access all 32 gigabytes of the system memory directly.
Precisely. And that unified architecture allows developers to run massive models locally that would instantly crash due to out-of-memory errors on a standard consumer NVIDIA card.
Wow. Okay, but CPU calculation is still slower, right? How do they mitigate that?
They use a technique called integer-8 quantization.
Right, quantization.
Basically, the standard 32-bit floating point numbers that make up the AI's neural network, they get mathematically compressed down into 8-bit integers.
So they're shrinking the model.
Yes. You trade a microscopic, almost unnoticeable amount of accuracy for a massive reduction in the model's memory footprint. And it significantly increases execution speed on standard processors.
The document actually codifies this whole philosophy in a phrase I loved: prioritizing throughput over latency.
Yes, that's a crucial distinction.
Because if you're building like a real-time conversational voice assistant, latency is everything. The time it takes to generate the first word matters. If there's a 2-second delay, the illusion of a conversation is broken.
Right, it feels laggy.
But throughput is about the total volume of work completed over a long time frame. And because this pipeline is a batch process that just churns in the background, latency doesn't matter.
Exactly.
Who cares if the local CPU takes 15 minutes to transcribe the audio instead of the 2 minutes a massive RTX 4090 GPU might take? You've already walked away to get coffee.
The user's time is liberated, and the machine's time is fully utilized. It is a total paradigm shift away from our obsession with real-time, synchronous speeds, moving toward asynchronous, highly reliable batch processing.
Okay, so let's actually trace that batch process. The document organizes the assembly line into 4 distinct stages.
Right, the engine room.
Yeah, let's open the engine room. Stage 1 is transcription and diarization. This is the foundation. It takes the raw audio and turns it into structured text.
And for this, the pipeline employs Faster Whisper, specifically pinning the large V3 turbo model.
Faster Whisper is essentially an optimized, stripped-down implementation of OpenAI's original Whisper model, right?
Yes, it uses the C-Translate 2 engine, which makes inference highly efficient on local hardware. And the large V3 turbo variant is chosen because it strikes the perfect balance, high accuracy, manageable memory footprint.
But the document notes that a raw transcript from Whisper isn't actually enough for what they want to do.
No, it's not. If you want those dynamic karaoke-style captions that pop up on screen exactly as the word is spoken.
Which is what every viral video uses now.
Right. A standard transcription model can't do that. Whisper typically only produces segment-level alignment.
Meaning it gives you a start and end time for like an entire sentence or a 5-second block of text.
Exactly.
No.
Segment-level data tells you a phrase happens somewhere in a 5-second window. But if you want a specific word to light up precisely on the syllable, you need word-level alignment.
Microsecond precision.
Yes. So to achieve that, the pipeline actually implements a secondary alignment pass over the audio.
Oh, a second pass.
Yeah, it uses a dedicated forced alignment model to cross-reference the actual phonetic sounds in the audio file against the raw text generated by Whisper. It forces a timestamp onto every single syllable.
That is incredibly intensive.
It is. And then the pipeline initiates a third process within stage 1, speaker diarization, using an open-source library called Pianote.
Diarization being the process of clustering the audio based on unique vocal signatures, right? Figuring out who is speaker A and who is speaker B.
Right. It turns a massive block of text into a formatted script with speaker attributions.
But wait, orchestrating the Whisper model, the alignment model, and the Pianote diarization model all at the same time? Wouldn't that introduce a massive resource conflict on a local laptop?
Oh, it absolutely would. The memory constraints of the unified architecture become a very real bottleneck here.
Because if you load them all into RAM at once, you blow right past that 32 gigabyte limit.
Exactly. And the document details this fascinating, almost violently aggressive memory management protocol to handle it.
What do they do?
The pipeline explicitly refuses to hold these models in memory concurrently. It loads faster whisper, completes the transcription, and then it executes a literal Python del command.
A del command.
Yes. It forces the immediate manual deletion of the massive transcription model from the system's memory.
Wow. It's essentially manually triggering garbage collection.
Okay.
It's forcing the Mac to just dump the weights of the Whisper model entirely to clear out the RAM before it even dares to load up the piano diarization model.
Right, because if it attempted to hold both in memory at the same time, the system would immediately hit its swap file on the hard drive, the performance would grind to an absolute halt, or it would just crash entirely with an out-of-memory exception.
That is just a beautifully choreographed sequence, like a really stressful dance of loading and unloading heavy assets.
It really demonstrates the developer's deep, practical understanding of local hardware limitations.
Okay, so stage 1 gives us a perfectly timed speaker-labeled text file. Then we move into stage 2, metadata generation.
The local brain of the operation.
Right. The system now has to synthesize a catchy YouTube title, a good description, tags, and timestamp chapters. And to do this entirely offline, the pipeline spins up a local MLX server.
MLX being Apple's open-source machine learning framework, specifically designed to run models efficiently on Apple Silicon.
Yes, and the pipeline feeds the data into a very specific large language model, Qwen 3.6 35B A3B 4-bit.
That's a mouthful.
It really is.
But Qwen is a highly performant open-source architecture. And at a 35 billion parameter scale, it actually has immense reasoning capabilities. It rivals proprietary cloud models like ChatGPT or Claude for these specific text synthesis tasks.
And that 4-bit at the end of the name indicates another layer of that aggressive quantization we talked about earlier, compressing 35 billion parameters so they actually fit inside a standard MacBook Pro.
But here's where we hit one of the most brutal architectural compromises in the entire paper.
Yeah, the data feeding process.
Right, how the pipeline feeds the transcript to this Qwen model. It takes this painstakingly generated millisecond accurate transcript from stage 1, and before passing it to the MLX server, it applies a hard crop.
A hard crop at exactly 60,000 characters. It literally just truncates the input text.
It just chops it off.
And 60,000 characters equates to roughly, what, an hour of spoken audio?
Right around an hour, yeah.
So if you feed this pipeline a 3-hour deep dive podcast conversation, the system is effectively blinding the LLM to the final 2 hours.
It is a severe limitation, but mathematically, it's totally necessary.
Because of the context window.
Exactly. Every large language model operates within a strict context window, the maximum amount of text it can process at one single moment. And as you increase the length of the input, the memory required by the model's attention mechanism doesn't just scale linearly, it scales quadratically.
Oh, wow.
Yeah. So pushing a 3-hour transcript into a locally hosted 35 billion parameter model would just instantly overwhelm the unified memory.
Computer would just give up.
Totally.
But the implication there is wild. It means the generated title, the summary description, the tags, they are synthesized exclusively from the first hour of the recording.
Yep.
If the core thesis of your entire podcast, the big aha moment, is revealed in the final 20 minutes, the metadata generator is entirely ignorant of it.
It has no idea it happened.
It's prioritizing system stability over comprehensive understanding.
The developer clearly determined that having an incomplete summary is vastly preferable to a catastrophic system crash.
Right. I mean, pragmatically, yes. And that pragmatic approach is really mirrored in how the pipeline handles chapter generation, too.
Oh, the failsafe.
Right. So the LLM is tasked with formatting the transcript into logical YouTube chapters. But we know LLMs are inherently probabilistic. They hallucinate.
They absolutely do. They'll skip sections or they'll fail to output the correct JSON structure and break the parser.
So to counter that unreliability, Stage 2 implements a failsafe heuristic based strictly on the raw audio timestamps. It monitors the silent intervals between spoken words.
Right.
If it detects a continuous block of silence that exceeds 300 seconds, a full 5 minutes of dead air, it automatically bypasses the LLM entirely and just inserts a hard chapter marker right at that timestamp.
Which is really clever because a 5-minute silence in a standard audio recording is a massive anomaly.
Yeah, nobody just sits in silence for 5 minutes on a podcast.
Exactly. It typically indicates a massive break in the recording session or a change of venue. Or, crucially, it's an artifact of synthetic audio generation.
Right, because the paper specifically mentions Google Notebook LM.
Yes, and those synthetic engines often stitch discrete topic generations together, and they tend to leave long, silent buffers between the segments.
So a 300-second silence becomes this foolproof, mathematically objective indicator of a major scene transition.
Exactly. It requires absolutely no advanced reasoning from the LLM to detect.
It's a brilliant low-compute fallback mechanism. If the complex 35 billion parameter model fails to understand the narrative, the dumb 300-second stopwatch catches the error.
It's extremely robust.
Okay, so the metadata is locked. We have the text, we have the summary. Now we transition to stage 3, video rendering.
Heavy lifter.
The true heavy lifter. This is where the pure audio and the text data are translated into a 1080p 30 frames per second visual file. And the architecture here relies on an interplay between two things, FFmpeg and a web framework called Remotion.
Now, FFmpeg is standard. It's the industry standard command line tool for media manipulation. It handles all the foundational audio ingestion.
Right, everyone uses FFmpeg.
But the visual generation is offloaded to Remotion, which represents a really fascinating paradigm shift in video rendering.
Yeah, because Remotion allows developers to construct video timelines using React.
Yes, React, the exact same web framework used to build dynamic websites like Facebook or Netflix.
Which means the developer is literally using web technologies, HTML, CSS, JavaScript, React components to visually lay out the video frames.
It's wild.
The millisecond accurate transcript from stage 1 gets piped into these React components, dynamically animating the text on the screen, perfectly synchronized with the audio.
And the way Remotion works under the hood is it essentially spawns a headless browser instance.
Like a hidden Google Chrome window running in the background.
Exactly. It renders the web code, and then it takes a high-resolution screenshot of that hidden browser 30 times every single second.
Wow.
And then it relies on FFmpeg to stitch those thousands of static images together with the audio track to create the final MP4 container.
But the inter-process communication, the communication between the Node.js environment running Remotion and the system-level FFmpeg binary, that requires immense memory buffer coordination, right?
It does. And this is where we uncover what might be my favorite part of the entire document. A truly absurd, highly effective piece of developer duct tape.
Oh, the silence hack.
Yes.
So stage 3 includes this mandatory pre-processing step where FFmpeg is instructed to forcefully append exactly 20 seconds of pure dead silence to the very end of the input audio file.
It intentionally bloats the duration of the media before it even passes it to Remotion.
Why? Why add fake silence to the end of your own file?
It is a direct response to a very specific edge case in how Remotion handles memory buffers.
Okay.
To avoid loading a massive multi-gigabyte audio file entirely into RAM all at once during the rendering process, Remotion utilizes a feature called Use Window Audio Data.
Okay, window data.
Yeah, it basically reads the audio file in sliding 30-second windows as it progresses frame by frame through the video timeline.
Oh, I instantly see the danger there. When you have sliding windows, what happens when you get near the end of the file?
Exactly. When the render reaches the final few seconds of the video, it attempts to pull a full 30-second window of audio data. But if the file is ending, and there's only, say, 5 seconds of audio left,
the byte range request fails to satisfy the 30-second buffer requirement?
Yes. The internal server encounters a boundary error, and it throws a fatal HTTP 416 range not satisfiable exception.
So the entire rendering process just crashes at the 99% mark.
Just dies right at the finish line because it mathematically cannot fill its final memory buffer.
And fixing an underlying byte range calculation error deep within a third-party React library's buffer management system, that is a complex nightmare task.
It would take weeks to debug and submit a patch upstream.
So instead of debugging the upstream dependency, the developer just applies a sledgehammer?
The 20-second silence.
Right. By appending 20 seconds of completely empty audio to the end of the file, they ensure that the sliding window always has sufficient mathematical runway to complete its final read operations without ever hitting the end-of-file marker.
It is so crude.
It is incredibly messy, but it guarantees that the pipeline executes successfully.
It perfectly encapsulates the ethos of a tool built for personal utility rather than, academic purity. It just works.
It just works. So the MP4 is successfully rendered. We have our video. The pipeline now enters stage 4, the upload.
And this is the very first time, and the only time, the system actually communicates with the external internet.
Right. Interfacing directly with the YouTube Data API v3, but transporting a massive multi-gigabyte video file from a local laptop to a remote server that is fraught with network instability.
Standard HTTP POST requests for large files are notoriously fragile. If you have even a momentary drop in your Wi-Fi connectivity, the TCP session terminates, and you have to restart the entire gigabyte upload from scratch.
Which is infuriating. So the pipeline mitigates this by implementing a resumable chunked upload protocol.
Right. It segments the MP4 into distinct 1 megabyte payloads.
Oh, tiny chunks.
Very small. The pipeline transmits chunk number 1. It waits for a successful 200 OK acknowledgement back from YouTube's server, and only then does it proceed to send chunk number 2.
So if your local network completely drops while it's uploading chunk 500, the system just retains the state.
Yes. And when your Wi-Fi comes back online, it seamlessly resumes transmission right at chunk 501.
It ensures absolute delivery regardless of how spotty your local network is.
Exactly. And once the entire file arrives, the API applies all that metadata we generated back in stage 2.
But the document specifies 2 really critical default configurations for this API call. First, every single upload is defaulted to a private visibility state.
It never publishes publicly.
Right, which is a completely necessary safeguard when you are relying on autonomous LLMs to write your titles and descriptions.
Absolutely. The pipeline refuses to just dump the content onto the public feed. It mandates a human-in-the-loop workflow.
The creator still has to log into YouTube Studio, manually review the title and tags, make sure the LLM didn't hallucinate anything crazy, and then manually toggle the video to public.
It's a smart safety net.
And the second configuration parameter is a hard-coded tag. Contains synthetic media, true.
Ah, yes.
The pipeline proactively alerts YouTube's backend that the video contains AI-generated material.
Which is very timely, because YouTube recently deployed incredibly strict policy frameworks regarding the disclosure of altered or synthetic media.
Right. They really crack down on undisclosed deepfakes or AI audio.
And given that this pipeline's foundational design is centered around processing Google Notebook LM audio, defaulting that synthetic flag to true ensures the developer never inadvertently violates platform transparency guidelines.
It avoids a potential channel strike. But, and I thought about this immediately, this reveals a major limitation of the current architecture. Because if I process a completely organic, human-recorded conversation through this pipeline...
It permanently flags your authentic voice as synthetic media.
Right. In a public open-source release, that Boolean flag would absolutely require a configurable toggle. But in this pre-release draft, it is completely hard-coded to the developer's specific reality.
And that hard-coded reality actually permeates the entire control structure of the pipeline.
Yeah, let's talk about the UI. Because we have this highly complex 4-stage asynchronous factory. But the user interface to actually steer this machine is aggressively minimalist.
There is no slick graphical dashboard, no web interface on localhost, no standard settings menu.
The configuration is totally decentralized. The authentication parameters, like the YouTube API client secrets, they just reside in a hidden .env file. Right. The runtime configurations, like picking which visualizer template to use, those are injected via command line flags when you start the script. The actual system prompts that guide the LLM's behavior, those are just stored as raw markdown files buried in a specific directory.
And the routing logic dictating which YouTube playlist the final video gets dumped into is just mapped inside a simple playlist.json file.
So how do you actually operate it? The document says the user interfaces with a TUI, a textual terminal UI.
Which is very retro, very hacker style.
Yeah, it renders entirely within the command line interface, utilizing ASCII characters to draw little progress bars and status updates.
It completely avoids the overhead of running a local web server just to render a GUI, which aligns perfectly with the pipeline's whole resource-constrained philosophy. Keep it lightweight.
But the true ingenuity of the control system, the absolute brain of the operation, lies in a singular localized file named runstate.json.
The state machine.
Yes. The document describes this architecture as a mealy state machine, which I envision this functioning similarly to a really robust finite state automaton.
Well, the pipeline has to rigidly track its execution context, because processing a 2-hour video locally is a very long-running operation.
Right, it takes hours.
And if the local machine experiences a power failure or a kernel panic or Honestly, if the user just accidentally closes the terminal window midway through the video rendering in stage 3, the execution just halts.
And in a standard Python script, restarting the process means starting from absolute zero.
Which is devastating.
You lose the hour you spent on transcription, you lose the hour you spent rendering, and you have to execute the entire linear sequence again.
The runstate.json file prevents that catastrophic time loss. It acts as a persistent memory module.
Right. So as the pipeline progresses, it logs the status of each discrete stage. Transcription is marked complete, metadata is marked complete, rendering is marked in progress.
And when the pipeline initializes, its very first operation is to parse that JSON file.
So it reads the state, it identifies that stages 1 and 2 are finalized, it recognizes that stage 3 was interrupted, and it immediately reinitializes the rendering process without repeating the prior heavy ML workloads.
It just picks up exactly where it left off.
And to ensure that this critical file isn't corrupted during a crash, the pipeline utilizes atomic file writes.
This is a really important detail because writing data directly to a file is actually very dangerous. If the power cuts mid-write, the JSON structure is left half-written. It's corrupted.
And the state is lost permanently.
Right. So the pipeline utilizes the process_xs.replace system call. It writes the updated state to a temporary hidden file first.
Okay.
And only when that complete write operation is totally finished does it issue the command to swap the temporary file's inode with the actual runstate.json file.
And the operating system guarantees that this swap occurs instantaneously.
Yes. It is mathematically impossible to corrupt the file. The state is either the old valid state or it's the new valid state. It is never halfway in between.
The architecture is completely airtight.
It is.
Which is exactly what makes the discovery of this glaring failure regarding idempotency so jarring.
Ah, yes. The idempotency flaw.
Okay, so idempotency is a foundational principle in robust API design.
Yes. It dictates that executing a specific operation multiple times should yield the exact same system state as executing it just once.
So if I run the transcription stage twice, I simply overwrite the local text file with the exact same text. The end state is identical. The transcription process is idempotent.
Right.
But the document acknowledges that stage 4, the upload to the YouTube API, completely lacks idempotency checks.
Because mutating an external state introduces massive complexity.
Right. So if the user restarts the pipeline and the state machine fails to recognize that the upload stage was already completed.
Maybe they intentionally cleared the state file to re-render a visual bug or something.
Yeah. The pipeline will not query YouTube to verify if a video with that exact hash or title already exists on the channel. It just blindly executes the chunked upload again.
It just fires it off.
And it results in a permanent external duplicate on the user's YouTube channel. A true idempotent system would require the pipeline to cache the specific YouTube video ID returned after the initial upload and inject a pre-flight query checking against that ID before ever initiating the transfer again.
The absence of that deduplication check is just a profound indicator of the software's current lifecycle stage.
Totally.
It is a tool built by a developer who implicitly understands their own pipeline's failure modes, and they actively navigate around them. They simply know, personally, not to trigger the upload twice.
Which brings us perfectly to the most illuminating aspect of this entire deep dive, the workshop reality.
It's skeletons in the closet.
Exactly. We are examining a document labeled pre-open source review and preparing a piece of highly customized personal automation for a public release on GitHub. It is a traumatic process of generalization.
It really is. And the document actually audits its own technical debt here, laying it all bare.
Yeah, and the most glaring omission, for any production-grade software, is the complete absence of automated testing.
0 automated tests.
None. There is no test directory, no unit tests, no continuous integration pipeline configured.
The author explicitly relies on what they call smoke runs.
Right. They basically just execute the pipeline start to finish, and if it doesn't crash, they assume the code is stable.
Which is fine for a solo dev. But in the context of a sprawling open source project where you have multiple contributors submitting pull requests, relying on manual smoke testing guarantees catastrophic regressions, you need automated scripts validating every single function upon every code commit.
The technical debt extends right into the documentation itself, too. The document notes a severe case of documentation drift within the code base.
This was really funny to read.
It was. So while the current execution path clearly utilizes the local MLX framework and the local queue model for metadata generation, the internal code doc strings, the comments written inside the Python files themselves, still reference sending data to the Claude API.
It's an archaeological artifact.
It is. It proves that in an earlier iteration of this pipeline, before the developer figured out how to integrate local Apple Silicon LLM inference, they were routing the transcripts out to Anthropic's cloud models.
They updated the functional execution logic to be local, but they totally neglected to update the surrounding documentation.
And that kind of drift causes massive cognitive dissonance for external developers who are trying to understand their repository.
And that artifacting isn't just limited to comments either.
Oh, right, the .env file.
The .env configuration file still contains a variable for an Anthropic API key. The document literally categorizes it as a stale dependency.
Leaving unused API key structures in a repository is a severe security vulnerability just waiting to happen. An external user might clone the repo, see that variable, and populate it with a live, billing-enabled API key under the false assumption that it's required for execution.
Unnecessarily exposing their credentials in memory.
Yeah. But the absolute largest barrier to open sourcing this project, the ultimate manifestation of "it works on my machine" syndrome, is found in the configuration of stage 3.
The video rendering stage.
Yes. So the rendering stage requires access to the Remotion visualizer project, the actual React code that defines the layout of the video. However, that React project does not reside within the pipeline's own repository structure.
No, it doesn't.
The pipeline execution script is hard-coded to target a specific absolute file path on the developer's local machine.
It's wild. It navigates up 2 directories.
Yep.
It enters a folder named 10 Obsidian Vaults, traverses into a 0 shadow vault, and targets a specific directory completely buried within the developer's personal note-taking ecosystem.
It is entirely entangled with the developer's private, encrypted Obsidian architecture.
Which means if any user cloned this repository today and executed it, the pipeline would immediately throw a fatal path resolution error, because obviously their file system does not contain the developer's shadow vault.
It's just perfectly tailored for one specific person's workflow. To transition this from a personal script to a public tool, the developer has to undergo a painful process of surgical extraction.
They have to decouple the React visualizer from their personal vault, modularize it, bundle it directly within the repository structure.
And replace all those hard-coded absolute paths with dynamic relative path variables.
And the hard coding extends way beyond just file paths. The system logic is littered with personal configurations.
Right. The document lists hard-coded personal URLs.
Specific internal network addresses like uplink.jcandle.de.
Hard-coded YouTube playlist target IDs.
And specific visual branding elements tied to the Kuro signal protocol permanently embedded into the video rendering sequence.
Open sourcing a project requires neutralizing the software. The developer has to strip out their own identity, replacing every single personal preference with a configurable agnostic variable that any user can populate.
It forces the developer to confront all the chaotic shortcuts they utilize to achieve their own functionality.
It really does. And I think this entire exploration reveals the true nature of software automation.
How do you mean?
Well, we began this deep dive by envisioning this pristine, invisible factory, right? Silently converting pure audio into polished video with the press of a button. But opening the black box revealed a chaotic workshop.
Very chaotic.
We found aggressive memory management just to avoid crashing the local unified memory. We found brutal data truncation limits cutting off transcripts. We found sledgehammer hacks appending 20 seconds of silence to bypass third-party buffer bugs. We found hard-coded paths routing through personal Obsidian vaults.
It is a machine defined entirely by its constraints.
Exactly.
By rejecting the cloud, rejecting GPUs, and rejecting multi-platform distribution, the developer engineered a highly specific, aggressively optimized pipeline that sacrifices theoretical purity for absolute localized reliability.
Yeah, it trades elegance for execution. I want to end on the broader implications of what a pipeline like this represents for the future of media, though. We are analyzing a system that completely eradicates the operational friction of content production.
Yes.
If a creator can capture a raw audio thought and a free local pipeline can autonomously format it, visualize it, chapter it, and distribute it with zero marginal cost, the intrinsic value of production value collapses.
That's a really profound thought. When complex visual formatting, dynamic captioning, and algorithmic optimization become fully commoditized and accessible via a single keystroke, they cease to be competitive differentiators in the creator economy.
Right. If the automated factory is free and the packaging is flawless for everyone, the only variable left to define quality is the raw material dropped onto the conveyor belt.
The thought itself.
Exactly. In a landscape saturated with perfectly generated, visually flawless content, perhaps the ultimate premium will revert to the authenticity, depth, and unstructured reality of the original human thought.
That is definitely something to mull over.
Yeah. Thanks for exploring the workshop with us. Until next time.